Hello and good morning to all of you. Thank you very much, Professor Mohammad Asif, for inviting me to this very nice conference. And thank you very much, Mr. Meena, for coordinating. Thank you so much. So, the topic which I am going to present today is beyond terrestrial, unveiling the future generation of non-terrestrial networks. My name is Dr. Bilal Ahmad. I am working as a faculty member in the Department of Electronics and Electrical Engineering at Middle East Technical University in Turkey. Before joining this university, I worked to a very famous and well-known research group in the domain of satellite communication from University of Bologna. So I worked there as a postdoc research fellow. Before that, I did my PhD again from University of Bologna in the domain of satellite communication systems, specifically in non-terrestrial network systems. I have been involved in several European Union funded projects. So most of the work which I'm going to present, I mean, not most, I mean almost all of the work which I'm going to present today is part of European Union projects. So I worked in a very close collaboration with University of Bologna. And a very thanks to my professor at University of Bologna, who is also my supervisor, Professor Alessandro. So in the beginning, I'll try to make some concepts very clear to you, so that once we go deep into the presentation, you know these sort of concepts. So in wireless communication, we have two types of communication. One is terrestrial networks, for example, 4G, 4G LTE, 5G, 6G, and who knows what is going to be evolving in the next several years. So, I mean, you already know about these networks, you get high data rates, and I mean, these networks are amazing. But then there is another example of connectivity, and these type of networks are known as non-terrestrial network systems. So previously, I mean, satellite communication was very much known for its uh, broadcast television channels. So we usually took into account satellite communication as geo synchronous Earth orbit satellites. Then for the navigation, we used to work on medium Earth orbit satellites, and then we had LEO. But now, you may have gone through the literature, state of art, where you have unmanned vehicles, you have drones. So the classification is very simple. You look up to the sky, and if you are getting the connectivity from the sky, then you classify this as non-terrestrial network systems. So once you start comparing, okay, so terrestrial network systems and non-terrestrial networks, once you start comparing, both of them are very different to each other. How they are different? So terrestrial networks involve densification. So okay, you need to have more equipment on ground. You have base stations. Once you go to satellite communication or non-terrestrial network systems, you need to be launching a satellite to the sky, and this is a very difficult process. Plus, you have something which you don't have command. So if you fly a rocket and and the satellite is being launched, so then what is going to be happening? Okay, so this is something a one point design. You design something, you float it, the satellite, and then that's it. But what is the importance of your non-terrestrial network system is that you know that you have 70% of water, and then okay, your ground and earth is not flat. So what you need to do is you need to be having two mobile towers, and they need to be line of sight. So if they are line of sight, then yes, you are going to have a communication. But you think about this aspect, this is a very challenging sort of thing. Okay, instead of this, if you are looking up to the sky, whether you are in the ocean, uh, wherever you are, if you look up to the sky and you manage to get connectivity, the problem of connectivity is being solved. And then in terrestrial network systems, there can be several base stations after several kilometers. So I'll take you to a very nice calculation where you need to find, okay, how many base stations for terrestrial networks are required to cover an area of 2 into 10 raised to power 6 square kilometer with the base station covering a radius of 1 kilometer. Okay, so if you do this calculation, what you see is that 6.30 million base stations are required covering a radius of 1 kilometer. I mean, think about the whole universe. I mean, there are places where you are unable to mount the space station, and this is quite a very massive number. So, what are going to be an alternative? So, the alternative is, let's suppose, okay, so at a height of, let's say, above 36,000 kilometer, if you have a floating repeater, you can cover one third of the Earth. So this is something which refers to geosynchronous orbit. Now, satellites, what are they? Okay, so why there is need to have satellite communication or non-terrestrial network systems. So base stations are less than 100 meters. And if you want to cover more geographical coverage, we need to increase the height of the base station. And can you mount an antenna at a height of 36,000 kilometers? So this took us to 𝗕𝗲𝗃𝗧𝗏 Clarke. Okay, in 1945, he presented a seminal paper, and what he said that at a height of 36,000 kilometers, if you have three microwave repeaters in geosynchronous orbit, you can enable intercontinental communication. So simple, what you do is you with the help of a rocket, what you do is you take this floating repeater, and this satellite is nothing but a microwave floating repeater. So what are the advantages and disadvantages? Okay, so once you compare it with terrestrial networks, there are a lot of advantages. For sure, there are so many disadvantages. And what we see these disadvantages as an opportunity. So you can think about your carriers and requirement of high reliable design. You need to be having high reliability. So things like FPGA mounted on satellites, it is a very nice and new dimension which is, I mean, taking existence in so many European Union funded projects. One point failure. So okay, so how you are going to fix that? Okay, so reconfigurability is something. It also requires heavier launching rockets. So people from electrical engineering, aerospace engineering, they are working on this sort of thing. Again, on-board power supply, electronics, electrical engineering to work on this. Tracking and monitoring of satellites, people from computer science, computer engineering, electronics, electrical engineering, all of them, they can work on these sort of domains as well. But advantages, it provides a reliable solution to the last mile problem. You don't have to dig the roads. So it is easy to set up once you compare it with terrestrial networks. For disaster, for defense, once you have nothing, you look up to the sky, you get the connectivity, and here is your solution to the problem. Fairness of services, so video on demand. Long life, okay. So could be 20 years, 25 years, depends on the manufacturing people. So as I explained before, okay, so the satellite is nothing but a microwave repeater. So you transmit your signal to the satellite, then you need to have an amplifier, and it sends your signals back to the ground. The most important thing is, of course, the propagation medium. Okay, so the propagation medium in your non-terrestrial networks is different as compared to terrestrial networks. Why? Because things like rain, atmospheric losses, barometric pressure, oxygen, nitrogen, which does not make sense in your terrestrial networks, but they do make sense in your non-terrestrial networks. So channel modeling is something which is again a nice domain to be working on it. Then the purpose of this slide is just to recap something. So you know ITU do the spectrum region-wise distribution, and what we are seeing is the bands from L to Ka. So the voice communication is being done at 2 to 4 gigahertz, and for broadband 26.5 to 40 gigahertz. So the European projects which I am going to introduce. For the voice communication, we did this sort of, we considered this sort of frequency, and then for the broadband, we consider this sort of frequency. And one thing, what we require is that we need to require a higher data rates. And for higher data rates, what you need to be doing is you are required to go to the higher frequency. So higher frequency means higher throughput. But okay, so if you are having higher frequency, what you are going to get is shorter distance communication, right? Because of shorter wavelengths. So how to improve the coverage? Then you get into the domain of multiple input and multiple output systems. So you go for either cell-free MIMO. This is something, I mean, this is a very interesting domain, and you see a lot of research going into multiple input and multiple output system. But of course, spectrum is a very sacred resource, and the topic which I am going to discuss is also interference management and mitigation techniques, which is to effectively utilize the radio spectrum. So now we have some understanding about terrestrial and non-terrestrial network systems. Now, what I want you to be referring is that you see, okay, from 2.4 kilobits per second to 1 to 10 gigabits per second. This is something the expectation we are having from 5G. And from 1G to 5G, generation of mobile technology attempted to meet the needs of end users and mobile operators. And the new development of data-centric automated processes may exceed the capabilities of 5G systems. And we are calling it as a new wireless generation. So, 5G was evolved considering three use cases: ultra-reliable low-latency communication, enhanced mobile broadband, and massive machine-type communication. But in 2030, we are going to considering something which is rural connectivity, public safety, network resilience, network automation. What is going to be the role of public energy and environment, reducing carbon dioxide emissions? So this is a very nice paper, and I strongly encourage you to go there. This is from University of Bologna. We have people from 𝗕𝗲𝘃𝗧𝗲𝗍𝗔, and for sure, I mean, there are so many other people from well-known industries. So please go and read this sort of thing. But the crux is that, okay, the need of 6G or the enabling of 6G is due to the advancement of your artificial intelligence and machine learning. So now we know that how much internet is useful. Okay, so the purpose of this slide is, okay, even those countries who are progressive and they do have 5G, you see in 2019 there was a hurricane in United States of America, and what is the outage in terms of network connectivity? So people were there out of internet, even America. Okay, they have this problem of network congestion. Then if you consider a football stadium, so how you are going to fix this sort of thing, even if you are providing 5G connectivity or maybe in future 6G connectivity. So it is directly coupled to the geographical area. What you need to do is you need to be densifying the network. So is it a good and reasonable way to bring more equipment to the stadium? Okay. So in 2018, 55% of the global population lived in urban areas, and 67 had mobile subscription, but only 3.9 billion people were using the internet. So majority of the people remain unconnected with this 5G, 6G, though where these 5G and 6G networks are being deployed, people are getting very good data rates. But then the problem is, when there is a disaster or there is any problem, you have no access to now the importance of non-terrestrial network systems. So 3GPP started working on non-terrestrial networks in 2017, and this is the first release where non-terrestrial network use cases were considered. And they now everyone, okay, admire that satellites is a viable solution, and this is a solution which is not constrained by geographical environment, and we need to be providing connectivity because this is the fundamental right for everyone. So what you see is GEO, MEO, LEO, and you are coming down to 100 meters. So from 35,000 kilometers, you are coming down to 100 meters. Okay, so advantages and disadvantages. We keep this sort of things in a very simple fashion. So if you are there in GEO, you require 3 satellites. Okay, that is something which we explained earlier. So you have less number of satellites, means you are going to have less number of handoffs. But what is the problem? As I said to you before, the satellites are nothing but a microwave repeater. So you think about this distance of 35,000 kilometers, which is bringing a lot of latency, which means that the applications such as imaging for high resolution or the communication applications which require low latency are not going to be practical with these sort of orbital satellite. So for sure you need to be coming down, and LEO is something which is a huge attention. And then you see Starlink, okay, they work on VLEO. So what you need to do is to have a mega constellation, let's say. But what will happen is, yes, you are going to have large number of handoffs. The gateway cost is going to be very expensive, but the propagation loss is going to be least. And because of the least propagation loss as compared to your geo satellite, what you are going to be achieving is low latency communication. So now, okay, whether to go for terrestrial networks standalone or to go for non-terrestrial networks standalone. Then, okay, because we are academicians, so yes, what we realize is that we want to have research towards internet for everyone, and that is something which brings us to a collaboration. And this is something which is a very, very important research domain, and for the next 10 to 20 years, trust me, this is not going away. So what is this? This is the integration of your terrestrial networks with non-terrestrial networks. So you deploy your terrestrial network. In case of a failure or in case of any problem, what you do is you get backbone connectivity from non-terrestrial networks. And the key enabling technologies for the next generation of wireless communication, which is 6G, is antenna design advancement, spectrum management, channel model, which could be millimeter wave or terahertz communication. Okay. Again, I would strongly advise you to go and read this paper, which is from Professor 𝗕𝗲𝗶𝗶𝗹𝗶𝗹 is from University of Bologna, and he was also my co-supervisor. So this is a very, very nice white paper which reflects to architecture, services, and technologies towards 6G NTN systems. Okay, so what are the challenges and opportunities? Uh, and this is something which is leading us to my contributions towards the European Union projects, which I mentioned before. So, spectrum for satellite communication is limited, and you know that to make use of the spectrum effectively and efficiently, what we do is we use frequency reuse techniques. And to improve the transmission data rate, several spot beams are generated on ground. Now, these days, you find that aggressive frequency reuse are being deployed. But because of this, what you are going to get is co-channel interference. So, if you want to improve the sum rate capacity of the system, what you need to be doing is you need to be mitigating CCI, which is the co-channel interference. So, you may, I mean, try to think about interference mitigation by the illustration of this nice figure. So what you do is, let's say for simplicity, you have a standalone LEO satellite at a height of, let's say, 600 kilometers. Then you have several spot beams for the coverage. Uh, and then what you are going to have is a large number of users. So what is this problem? This problem is that you have so many number of users uniformly distributed. I mean, in practical situations, these are not uniformly distributed, but because we have to consider, uh, we have to build the preliminary. So what we say, okay, these are uniformly distributed, but what you see is that the number of users are very, very high as compared to the resources of your satellite. And by resources of satellite means what? The antenna element. So even if you are mounting a uniform planar array of 32 cross 32, which gives you 1024 or 1024 antenna array elements, and then you are having 1000 users, so this equation does not satisfy. Okay, so this type of problem is known as NP-hard problem. So how to solve this problem? So what we suggested is that, okay, what you do is you have several time slots, and for every time slot, what you need to be doing is you are going to be performing some clustering algorithms. What these clustering algorithms are going to be, for sure we know that these are going to be ending up with suboptimal solutions. Okay, and then what we also need to be considering that okay, these are European Union projects and we need something very practical. So what we need to be doing is what, to have some practical solutions which do require low computational complexity. So the problem is simple: investigation of user scheduling algorithm. I mean, the problem is simple, but the solution is not simple. And what we really wanted to do is to maximize the sum rate capacity. So in the state of art,
we did a very,
for
very
sure you
massive
need to be reading
investigation
all
at
these
University
papers,
of
but I
Bologna.
will
We
try to make
investigated
you
each and every bit of user
equipped with
scheduling, and
several
now
concepts. So once you go
we
and
are
you try
at
to
a
read
stage
these
where
papers,
all the
you are
scheduling
familiar with
techniques
them.
which are being
Okay, so
adopted
there
in
are two
satellite
types of scheduling
communication
algorithms. Once we discussed
are most of what
non-terrestrial
we
networks,
have presented
and
as
I have
University of
explained to you
Bologna.
that
Okay. So why user scheduling
the
is
channel
very
model for
important,
your
I
non-terrestrial
already
network is
explained to you.
different.
If
Why?
you go to
Because
the
you
state
take
of art,
account
you will find there are
um,
two different types of scheduling
rain
techniques
attenuation,
which are being done in
water
satellite
vapors,
communication.
nitrogen, etc.
One is known as
So
user
there are
selection,
two types.
and
One is
another
user
one is known
selection, another
as
one is
user
user
grouping or
clustering.
clustering. So
So
user
user
selection scheme is
selection
something,
is
okay,
typically
what you do
performed
is
once you need to find
you
out the
select
performance
the
field. Okay, but the
best
problem is that
users
these are
having
not
the
going to be
best
served at
channel gains,
the
and you serve them.
number of users.
But then the
So
problem
the
is
channel
with the
conditions,
channel.
they
So if you are going to the satellite
I mean
communication channel, what you see is
they
that
change. Say
you
for
serve
example, if there is a rain, if there is no
a
rain,
set of
so those
users,
users who
they will
want to be
remain
served,
there
they will
forever
remain star.
until and unless there
And
is
then there are user
some
grouping and clustering. Before
violation
we
of the
went into this
condition. So
sort of
let's say, I mean,
topic,
those users are
investigating
going to
for
be
the
remain
European
over
Union
there if
projects,
you are
we
not having
investigated
any
the
rain.
state
So
of art,
you
and
have to
a
wait
very
for the
well
rain.
known
Only then the
algorithm is
channel
MEDAC,
conditions are going
which
to
is
be
being presented
changed. So it
with
means
by
that you are
Andreas
unable to
Law.
serve all the
Uh,
users. That is the
and
problem. So then we went on to
and
user
what
grouping and clustering
basically happens at
algorithms,
that
where
that you get
we
a
said,
very
okay, what we
suboptimal
do is
solution.
we are going to have different time slots. For each and every time slot, we will try to find the best users such that they they are totally orthogonal to each other. Why? Because we want different users to be there. If we want to have same set of users to a cluster, then what will happen? It will be a downgrade or degradation of the performance. And what is the performance? It is your spectral efficiency, bit per second per hertz, or your throughput, okay, bit per second, or your sum rate capacity. So, so what we did is we started our journey. We started uh, re-implementing some of the state of the art, and this MEDAC is a very novel algorithm. So we try to compare our proposed solutions with this sort of algorithm most of the time.
This is something which refers you to the path loss. So you see, for terrestrial networks, the path loss is different, but you need to be adding these two losses once you go to non-terrestrial networks. So now coming to the system model, which we adopted in the European Union funded projects, was a multi-beam LEO satellite. Then we took account ITUR recommendation, and then what we also considered was 3GPP specification. So the entire summary is going to be what, that we wanted to get a channel matrix, and based on the channel matrix we wanted to consider a decision policy where we effectively use this sort of decision policy, and then we clustered the users such that to improve the maximum sum rate capacity of the system. Now this is a very practical channel modeling thing. It take account all the practicalities, and okay, and then what happens is that we have several clusters, we make them sets, then we perform feed level beamforming, okay, uh, and then okay, the problem which we faced was that once we do this time division multiple accessing, uh, what we have is different time slots. So once we found cluster of users, what we find was that they are not equal in numbers. So maybe here we have more number of users, here we have less number of users. So we need to be having some very important and challenging thing, which is the weightage of the cluster.
This led us to a very novel concept, and which was to use graph theory. And graph theory is something which has immense utilities in every field. So what we said was, okay, we have number of users which are very large. So we said, okay, now we have number of users and we want to construct a graph, but how we are going to store this graph, because the computer does not know what a graph is. And once we have the graph, how we are going to decide, okay, which users need to be in cluster 1, 2, and how many total clusters are going to be there. So as I said to you, this is NP-hard problem and we are not getting the square matrix. So what we did was to first we consider the channel state information, and then we computed a coefficient of correlation matrix. Based on the coefficient of correlation matrix, what we did was we found the threshold of the graph. And once we found the threshold of the graph, what we found was a clique. So a clique is defined as the largest network within a graph. These user scheduling algorithms are presented in DynaSet, which is a European Union funded project, and it's been completed. My PhD was supported by this project. University of Bologna was the coordinator. University of Parma, Martel, 𝗕𝗲𝘃𝗲𝗀𝗧𝗏, spectrum. We all work together to come up solutions for dynamic spectrum sharing and bandwidth efficient techniques for high throughput MIMO satellite systems. So I would strongly suggest you to go and read the website of DynaSet. And what user scheduling algorithms I explained to you. This was presented in a very prestigious conference, ASMS, in 2022. So we took a channel matrix, we computed the coefficient of correlation matrix, we found the threshold, we optimized, we found the clique, which is the maximum clique, and then we created this joint set. Then we further investigated more algorithms, and then what we presented in 𝗕𝗏𝘃𝗧𝗲𝗏 6G Summit, again it was a part of DynaSet project. So we considered location-based clustering. So once you go to non-terrestrial networks, not necessarily you need to be computing the channel state information. So what you can do is maybe you consider what the location based clustering. So this is something which we investigated and we compared with the position based random scheduler, which used to find a constant number of users in every cluster. MEDEC is something which I explained to you. This is being presented by NTOS. This is non-graph based solution, and we compared this with CSI based maximum clique as well. So we did threshold optimization. We try to find mean cluster size. You see in the random scheduler, it is 91. But this is an important finding comparing CSI with distance-based max clique. So we were having an improvisation. Again, I would suggest you to please go and read this nice paper. Then this ended up our journey in DynaSet, and we went to another project which is 6G NTN. And this is a very massive project. Maybe I mean by the end of next year this project will be finished. It is on the last stages, and you see orange 𝗕𝗲𝘃𝗃𝗃𝗃 space. Quite a lot of industries are there, and this is a very massive project. German Space Agency is also there, and University of Bologna is the one who received this funding. So for this, we presented in ICCCI 2023 improved clustering. So what improved clustering was, basically, I mean, we were trying to find the threshold optimization for the entire graph. Differently, what here we did was, for every time slot, we tried to find the gradient to a very nice results. This paper also took account Ka band. Previously, the papers which I explained to you, or the work which I explained to you, which are part of the projects, considered S band. So, and then we also modified the MEDEC algorithm, which is non-graph based. It was not our algorithm, but what we did was, instead of finding the coefficient of correlation matrix, we migrated the design to a distance based MEDEC. So this paper was presented in a very prestigious conference for Ka broadband communication, and it was nominated for the best paper award. Now this paper is also invited for IJSCN, which is a very prestigious wireless journal. You can go there and you will find it a very interesting paper. Then we also considered that okay, we need to be working on computational complexity. So as I explained to you, this is a very important subject. Why? Because in graph you have nodes and you have edges. So what we did was we solved this as a graph coloring problem such that to reduce the computational complexity. And this paper is presented as location-based user scheduling through graph coloring, and we went from the traditional spot beams to self-read. The key contributions are Dynaset project, 6G NTN, 5G Stardust, and Eager. What I really want is, apart from my contributions, what I really want you to be considering is to go on LinkedIn and go to these websites and see what these projects are doing. This also end up to my presentation for sure. I mean, it was just 20 to 25 minutes. I have no idea. Maybe I am a bit longer, maybe 30 minutes. At the end, what I will also like to mention is that here at Middle East Technical University, we are looking for collaborations as well as I have a project which is a funded project. So I am looking for resources in terms of scholarships for master students, and the topic is going to be secure satellite communication systems. If you need any information you want to apply, please feel free to communicate with me using my email.